So good afternoon to one and all. Again, we joined in QT-09, Engineering Foundations of Quantum Technology. And today's topic is about context-free language and push-down automata. Okay, so before starting today's lecture, I try to revise what happened between 2 days. 2 days. So this is the first day, 16th April, about theory of computation. Okay, we started about talking abstract model of computation. Okay, so these are the pioneers, key pioneers in the field of theory of computation. Okay, so if you have time, please go through each and every one of these great personalities. Okay, so we discussed why we need to study theory and what is the role of theory in computer science and what is the meaning of computability theory. So it evolved from 1932 until 1950. Then slowly we going to study about complexity theory. It started from 1960 until present. Okay, so which give insight about theory of computation. So in much more deeper fashion. Then we discussed modeling about a computation, how we can do a model, a abstract model. Okay, so there are different types of model of computation started from 1930 until 1980. So after that, we evolved into supercomputer. Today, we emerged into quantum computing. So that is the historical line. Okay. So in order to understand theory of computer science, we need to understand the language as well as grammar related to that particular language. So it is just like our normal language. So from ancient time, people tried to compute astronomical events. So in order to planning their day-to-day life activity and seasonal monthly activity from agriculture until each and everything. So there are different types of computer we went through, different forms. To understand abstract modeling of computation, we try to understand the thermodynamical example. So it is a heat engine. So this example tried to abstract the entire heat engine. So based upon that, we can build a much more complex system like nuclear power plant, which is based upon the same heat engine. So in such a way, we are able to create a Carnot engine. Okay. So if you are able to do a Carnot engine in an abstract way, so this will lead to abstraction of computation. Okay. So the basic idea of computer is about this normal input computation machine and it will yield output. So it contains severe goals, major goals, and what computer can do and what is a computer. We need to understand each and everything. So in 1936, a major shift happened in theory of computer science by Alan Turing, who is a mathematician. So he modeled a computer. So he modeled a computer in abstract way. So before World War II, humans are doing all these calculation. So you can call humans like a computer. So they do mechanical computing. So all of us, we are doing mechanical computing for smaller number of problems or small size problems. So most of us will do problem solving use pen and pencil, pencil and paper. So we can abstract all these in a infinite or finite length of tape. So we can convert all those into symbols. So in a particular way, we can able to model brains, our human brains. Why we go for machine? Why we are seeking for machine help? Because we have limited amount of memory. So this is the basic model of Turing machine or Turing model. So where you can have multiple states. According to the input, it will move left to right. So it will create to make a good model. Okay. So this is our ambition. We need to create a universal Turing machine which will solve all type of problem we have. So it is a ideal one. So far we are not able to achieve a universal Turing machine. Okay. So these three are very important questions we need to ask. What is a problem? What is a machine? And how we are machine going to solve a problem? Okay. To solve a problem, there are different kind of machines. So you can consider you need to travel. So you have multiple options. Either you can go by walk, or you can go by cycle, or you can go by a bike, or you can go by train, bus, or flight. Okay. So depends upon your choice, your traveling experience, speed, performance will vary. So we discussed about finite problem, and we discussed about output, how to map our output to the given machine. So I will show this diagram. I need to correct this diagram. Sorry about that. Then we discussed about automata theory. We have different types of computation model, CPU along with memory, and it contains so many different kind of memory. And we went through some example how it is getting operated logically. And finally, a machine, a abstract machine, if it is able to perform something useful, okay, for your given problem, then you can call it as an automaton. Okay, so you can compare automaton to a robot also. So robot is designed for doing specific task. So based upon this, you can have different kind of automata. So yesterday we covered about finite automata, and today we're going to cover about pushdown automata. So final form is about Turing machine. Okay, so what is the major difference? Finite automata doesn't have memory. Okay, pushdown automata have stacked memory. Turing machine have random access memory. So you can consider your computer like a Turing machine. It contains random access memory. So these are the graphical architecture. And we can classify the power of automata according to your machine architecture. Then we visualized computer like a transition function, like a mathematical function. Okay, you can consider your laptop or computer like a mathematical function. It will do some transition. If you are giving some input, it will do some transition. So to talk with your computer, we need to have a language. So language is depicted by capital letter L. Okay, language will contains word. Language will contain sentence. Okay, so the whole set of alphabet you need to depict with sigma. Okay, so you can say word with the help of W, which is contains strings. Okay, each and every letter you can say with the letter symbol called S. So if it contains all set of sentence, you can consider like capital V. Okay, so multiple possibility, you can put it like a V star. Okay, if your language contains empty string, then you can denote with lambda. So each and every textbook, each and every material, these notations will differ. Okay, so grammar in the short form, you can depict with capital G. So based upon this, you can construct a four tuple. Okay. Grammar contains V. So V means all your possible sentence. Okay. T means it is a terminal. So S means it is a sentence. P means it is a production. So P will produce your words, your sentence, your paragraph, likewise. So at some part of this structure, you have optional, some part you might have alternative. So in such a way, you are able to create a sentence. Okay. For the same sentence, you can have a different possibility according to your choice. So take an example of the large rabbit So here rabbit is acting like a noun. Okay. So before rabbit, you can choose either large, small, medium, according to your choice or according to the scenario. So after that, you can choose verb hops. So you can use different types of verb hops, right? So after that, you can mention how quickly or how slowly. So likewise, you can frame a sentence. Sentence should be meaningful because it need to follow grammar of that particular language. Okay. So this is one more example. This is one more example. The same sentence you can have a different combination. So likewise, if you know your language, if you know grammar of that language, then you are able to produce meaningful sentence. So this is for a small automaton. So you're starting from sentence yes. So yes will contain small a and capital A. Okay, where a capital A will contain double small a. So you can replace that with double small a. Okay, so look at the grammar. So this is the grammar. So yes tends to small a and capital A. Okay, we already discussed just for revision. If I keep on talking, today's topic we cannot cover. So these are the types of grammars. Today we're going to discuss a little bit about this. And these are the general concept of automata theory. We discussed about symbols, we discussed about strings, and we discussed about group of alphabets, which is a set called sigma. And you can do a lot of operation within the given string. You can able to add two strings, which is called concatenation. And you're able to reverse the given string and you're able to find the length of the given string. And you can concatenate two words, then you can be able to identify length of the given string. Then there are a special type of strings available in the language, which is called lambda. Lambda means empty and null. Okay, so you can find a substring within a given string. So it will give an idea if you want to find some words or some patterns. So this will give clue. So I can have prefix and suffix in order to generate a particular sentence or particular word, just like noun, prefix and suffix in English. And you can generate according to the power given for the string. Okay, take an example of this example, and we are raising to the power 2. It means it will generate for 2 times. It will get multiplied. And this is the star operation. Star operation means each and every possible outcome of the given language set. And this is one operation called plus. So the null symbol will not come, the empty symbol will not come, everything will replicate. So we discussed about the language. So ABC is a valid string, invalid string. Cab is a valid string. It does have some meaning. Okay, if you are generating some word, generating from word, it should have some meaning. You are asking about this. So it is not multiplication. It is a generation of the same sequence twice. So we discussed about the language. Then we discussed about all these things. It is keep on repeating. So I will repeat each and every concept because audience need to get familiar. More if I'm revising, more you will get stronger. Star means all possibilities. So that is why I'm discussing. So look at this. We have sigma. Sigma contains A comma B. So we have two letters. So E star means you can combine these two letter and you can produce n number of combination. Okay. So this language contains lambda, empty space. Okay. A as it is, B as it is. You are combining A with A. So likewise, you can go n number of E's. N number of E's. So I explain, sir. I will explain grammar once again. Once again. So A, B, you are combining both A and B. Here it is not individual, you are combining together like a single word. So this grammar you are asking. So G equal to V, T, S, P. Okay. G is the grammar. Okay. V is the vocabulary. You can create words, right? Each and every word belongs to V. Okay. Yes. So T means terminals. So T is actually set of words. Okay. Set of words. So all these T will belong to your vocabulary. If you are taking any word, definitely it will belongs to vocabulary. Suppose if you want to find any word in your dictionary, so dictionary will contain T. Exactly. Okay. So S is some special non-terminal. So it is like a starting symbol. Okay. It will not end. So where T will end. So this is the basic difference. Okay. So P is like production. So according to your vocabulary, if you are producing a new word, according to your new word, so it is called production. So T is a valid word. Yes, T is a valid word. Great. Great. So this is about the first day of TOC. So we elapsed 18 minutes for revision itself. So yesterday we covered about regular language. So we discussed about how your problems will grow, and we discussed about computational complexity. We discussed about Turing machine, and we discussed about Church Turing thesis. So there is a test. So if you are giving a test for a human and to a machine, and according to the answer, you need to identify whether the result is produced by a human or a machine. If a machine able to surpass the human intelligence or able to mimic like human intelligence, then it will pass your Turing test. So if a machine able to surpass Turing test, then you can call that machine is an intelligent one, like parallel to the human. Then we discussed about algorithm efficiency. So if you do this analysis, then it is called time complexity measure. Then we discussed about polynomial time. So these are the examples because we need to revise, sir. Otherwise, audience cannot get the flow. Especially if you are teaching mathematics, we need to revise yesterday concept and day before concept. Then we discussed about NP. Okay, these problems are somewhat harder than polynomial time. Then non-polynomial time problems are there. You cannot solve within the particular amount of time and you cannot verify its answer within a particular amount of time. Take an example of chess. If there is no timer, so people will play for years. Okay. If a king is playing again a very good chess player, if king doesn't want to lose his game, then he can take any amount of time to play the game. So it will belongs to not polynomial time. Then we discussed about class P and class NP. Then we have a variation of classification of difficulty level. Okay, most probably we are concentrating within P and NP class. So where quantum computing will help us. Okay, so there are certain kind of classes P space and exponential where quantum computer not able to solve those kind of problems. So some problems still even quantum computer cannot solve. Then we discussed about theory of automata again. We discussed about Alan Turing in the second day. This is the historical perspective. We discussed languages and grammars. Okay, same. Again, we discussed all this stuff. Then we discussed how to use automata to form a algorithm design, to do a algorithm design. So this is the classification of that complexity. Okay, so where BQP will have the major contribution for quantum computing. So we had a good example for finite automata. Take example of on-off switch. So it contains two states, on state and off state. Initially, we need to start from off. So if you're pushing, you're doing some action, it will change into on state. Again, if you're pushing, the on state will turn into off state. Okay, so take an example of forming the word the. So the starting symbol is arrow mark, okay, with followed by a circle. Okay, so then we have a transition. When you first enter T input, okay, it will move to T state. So this is the transition. Then TH is intermediate. Once again, if you are putting H followed by T, so T followed by H, then you'll have TH state. So it is an intermediate state. Then if you are giving E, then again you will get one more intermediate state called THE. So according to your input, your state will get changed. Okay. Finally, you reach then. So this is a finite automata machine to produce word then. So to use this finite automata, you need to have a regular expression. It is called structural expression. Then we discuss the same thing in a different way. So this is the revise of day 1 and day 2, what we covered. So today's class, we're going to discuss about context-free language and push-down automata. I try to make it as simple as possible. So before discussing all these concepts, yes, sir, we'll discuss. Regular expression, I already discussed. Today, we're going to discuss regular language also. So regular language, it is a language perfectly suitable for finite automata. Okay, if you want to design finite automata, definitely it need to support regular language. Okay, on top of that regular language, we'll have context-free language. Okay, so this language is exactly suitable for push-down automata. So according to the language, you need to select your mechanism or machine or your logic. Okay. On top of this, you have context-sensitive language. So context-sensitive language is supported by language for low-bound automata. So all these have different kind of automata. Once you have one, you know what is automata, then you can understand the complexity of this. So finally, you will have recursive enumerable language, which is the language given for Turing machine. So if you want to operate Turing machine, definitely you need to talk with recursively enumerable language. So this language you can classify into type 0, type 1, type 2 and type 3 technically. Right? So I'll share this slide. In your free time, you just go through it slowly. If you don't know, just go to the material. So let us discuss about context-free grammar. Okay. So context-free grammar is a formal system used to describe or generate strings of a language, just like a regular language. So it is a different types of language. It is a formal system. It is characterized by production rules where a single non-terminal variable is replaced by a string of terminals or non-terminals. So if you are looking at the definition, you might have some confusion. But if you go through an example, it is easy to understand. So context-free language is an actual collection of all possible strings that can be derived from specific CFG. So if you can write a CFG for a language, that language is classified as CFL. So it is a very hard question, whether language come first or grammar come first. So put in the chat box. Yes, we'll discuss in our day-to-day life whether language will come first or grammar will come first. language will come first. Grammar will not come. So in practical life, initially, we try to communicate with some vowel sounds. So vowel sounds are common. Okay, A, O, I, even the primitive languages, even animals, okay, they will talk with these vowels, basic sounds. From the basic sounds, we have modification. Okay, little modification. Then we are fine tuning. Then we try to represent that sound by using some symbol. So in a language, sound will come first, then symbol will come later. Letters will come later. So most of the languages will have sound. Most of the languages will have sound. But few languages have written form. Few languages have written form. So which language doesn't have written form? So it will fade away. Okay, this is a very interesting property of your language. If you want to preserve language, then definitely you need to have a written form. Okay, so Sanskrit survived so long without the written form. Then finally they found a Devanagari, it is a script to represent Sanskrit sounds. Okay, it is a fascinating history about Sanskrit. So, but here, okay, we need to have a grammar first. According to the grammar, we need to produce language. So, in theoretical aspect, we are creating language for machine. Okay, so if you are writing language, initially you need to create grammar. Okay, in real life, it is in reverse nature. So, each and every time, grammar will evolve. So these are the components for context-free grammar. So context will have variables, context will have terminals, it will have production rule. Definitely it will have start symbol. Okay. So what is the key constraints? So rule must be in the form of a letter a variable A, need to tends to some alpha, some states, any combination of symbols. Okay. So what is the analogy? You can think grammar like a recipe. Grammar like a recipe. It is a word, sir. So you can consider it is a ending word. Ending word. Okay. So symbol always start with symbol, yes, but it will not end. So terminal will end. So that is the difference. Are you able to get? So I can point this word. Take an example of and. So A is the starting, yes, and D is the ending terminal. So whole word will be meaningful. Okay. So grammar is like a recipe. If you follow a recipe, you have very good food. Okay, very good variety. Okay, if people are not following that recipe, they cannot get as it is. They will have different form. Sometimes you will get good form. Sometimes you will end up with bad form. Okay. So what is the meaning of context-free language? It will accept PDA, push-down automata. To implement this grammar, you need to have this machine, push-down automata machine. So it will use stack memory. So if you are not able to recognize all these words, so wait for some moment. So we'll explain with diagram. Okay, so take an example of palindromes. So take an example of balanced parentheses. If you are writing program, so you can have balanced parentheses. So here is an example. We are starting parentheses. So this is the starting. Okay, so this is the ending parentheses. Ending. It means it is a balanced. It is a balanced one. If I forgot to put ending parentheses, so a user might get confused. User might get confused. Okay, mostly it is based upon programming language. So if you are creating a programming language for computer or device, then definitely you need to use for CFL format, this language. So as it is. Okay, so if the grammar is a recipe, then language is set of all dishes you can could ever make that recipe. Okay, so formally, if you want to define context-free grammar, again you need to have 4 tuples. Okay, G belongs to grammar. Okay, V tends to variables, non-terminals. Okay, so sigma belongs to terminal, and R belongs to production rule, and S belongs to stock stream rule. Okay, so variables could be intermediate. Variables could be intermediate. Okay, so always we need to start with yes. So this is an example for context-free grammar. So starting symbol followed by A comma B symbols, and R stands for grammar, and S stands for starting symbol. Okay, so here yes going to produce small a, okay, followed by yes again itself, followed by B, and we have epsilon. It is a special character. Okay, so this rule will produce AB. So this rule will produce AB. So what is the meaning of this? So this is the rule. This is the rule. So you can substitute epsilon for yes. Epsilon for yes. It means you can ignore this. You can produce AB. So likewise, you can produce n number of words. So you can produce AB, you can produce AA, BB, because you have format, right? So it exactly distinguish between AB. Are you able to understand this rule? Shall I repeat one more time? Okay. So take this rule. S going to produce small a followed by the same capital S, okay, followed by small b. Parallelly, you have option epsilon. Okay, combination is going to produce epsilon in between S. It means it will produce A, B. Okay, so next time you're going to produce S in between them. Yes, in between them. It means you need to have the same sequence. So it is dividing between A and B. It is dividing between A and B. So you can produce double A followed by double B. So the pattern is repeated over here. So likewise, you can produce triple A and triple B. So it is self-repeating pattern. So this simple rule will produce in such a strings in such a way. I hope is it clear now? Shall we move? Shall we move? Okay, great, thank you. So language generated by a CFG, it contains all strings derived from the grammar. Sir, I cannot repeat more and more because audience will fed up, because it is a starting string, sir. It is a starting string. Or you can say starting symbol. This is the set. So this is the difference. This is the set. Okay. So all these are belongs to set. Okay. So this is the starting. So what is the starting rule? You need to start from S and you need to produce A followed by S followed by B. Followed by B. Are you able to understand this example, sir? Okay. Thank you. Yes. The number of A and number of B should be equal. Okay, let me rewrite this rule. If S have this rule, A, S, B, B, okay, then followed by epsilon. Then it will produce A, B, B, okay. So next it will produce A, A, B, B, B. So likewise. So uneven number of A and B. Because we have one more term, right? So it will generate in such a way. So there are 3 A's, definitely it will contain 4 B's. So one quantity more than A. Yes, exactly. So all set of strings derived from the grammar. Okay. So it can be recognized by pushdown automata. So take an example of A to the power n, B to the power n. Okay. So try to produce a language out of this. So same. So yes, going to produce A to the power n, B to the power n. So going to generate set for this. So put in the chat box. Put in the chat box. So what are all the options you have? You can substitute n could be 0, n could be 1, and you can go on. So substitute and put in the chat box what you got. Exactly. Exactly. Yes. Yes. Great. So key difference is grammar will describe how strings are formed. It will explain, it will have set of rules. Okay. The language is result of applying your grammar. Okay. It contains a valid strings. And what is the analogy? Grammar is equal to recipe. Language is dish prepared by using that recipe. So grammar defines structure. Grammar defines structure. Okay. Language is outcome of that. So lambda will come. If your language have that option, it will come. If it doesn't, it does not come. So sometimes lambda is very important because you need to have space between your words. So it is very important to create compilers and parsing. Okay, if you are creating any computer language, definitely you need to generate all these rules, all these regulations to interact with your language, to compile your language. Okay, if a person doesn't know grammar, he cannot speak in proper form. He cannot communicate efficiently. So almost we are lack of time. So what I will do, I will go for some more examples. Yes. So far we discussed about grammar and language. Now we're going to implement that concept by using pushdown automata. Okay. So we already discussed uh, automaton. I'll share, sir. I'll share. Definitely, I'll share, man. Okay. So pushdown automata contains a infinite input tape. Tape you can imagine like a cassette tape. Earlier days tape we are using, right? You can consider like that input tape. So in the tape we are recording our information. We are recording our information. So here you can find A, B, C. Likewise, you can record your information. Okay. So if you want to write instruction, then you need to press record button. Okay, most of us we know from previous generation we are using tape recorder. Okay, you need to press the recording button along with play. Then only you are able to record something in your cassette tape. Okay, so here you have finite control. So this is your automaton. Okay, finite control have some transition functions. So if you are pressing this button, it is like controlling your machine. Okay, so each time if you press that button, the state of your machine will get changed. If you are playing, it is in play state. If you are pressing pause, it will stop. Okay, if you are pressing stop, actually it will pop out. So there is a difference between pause and stop. Okay, so here we are using a stack. Stack you can consider like a box where you can store. Okay, whatever you are dropping over there, it will go down. It will go down. It is like a empty box. Okay, so whatever you are putting in that box, okay, the last put item will come in the top position. So like finite automata, deterministic finite automata, we can able to implement a regular expression in order to implement context-free grammar. Okay, so you need to know about your language, then only you need to choose your machine, kind of machine to solve your problem. Okay, so additionally, what you can do, you can use infinite amount of stack. So mathematically, if you want to solve a very big problem, then you can go for infinite size. So I can going to visualize pushdown automata with a schematic diagram. So we have input. So we are giving input for our machine. So this is our machine. So our machine contains finite state control. Okay. So in bottom we have a box. So consider this is like a box. This is like a empty box. Empty box. Okay. So this is called stack. So this organization is called stack. So it is a logical view. It is a logical view. Okay. Your finite state control machine will read input by symbols by symbol. Okay. Each and every time the instruction will vary. The input will vary. So all this input you can write through the stack, write through the stacks. Okay. Based upon the input, okay, from the top of the stack. So you can do two operations. So here you can notify, you can do two operations, read input, or you can write input. You can write input. So based upon this, according to the system architecture, either it will accept that pattern or it will reject that pattern. Okay. Suppose if you want to create a word to accept dad. So this is the word your machine need to accept. So you design a machine in such a way to design to accept the word dad. Suppose if you are giving input, dad, then what happens? Your machine will read one by one. So first it will read dad, then it will write to your stack. So what happens? This is your first input. D. The D will go bottom of your stack. Okay. So you are giving the second input called A. Okay. So your machine will read input A. Then it will write that information to your stack. It will go top of your D. So what it means, each and every time you need to monitor where is your top. So initially it is in bottom. So your top is in 0. So after D, your top is over here. Okay. After A, your top is over 2. So these are the positions. So this is 0. This is 1. Imagine this is 2. Okay. So last, what you are giving one more input called that 3. Okay. This is the third input. It will write over here top of your A. So top will come over here. Okay. So here if you are putting DAD. So this is about a write operation. Okay, so what happens if your machine want to read your data? Then you need to do in reverse order. So I will erase all these inks, all these inks. Now, if you want to perform read operation, you need to know where your topping is existing now. Your top is existing in third level, so this is 0th level. Okay, your top existing third level. Now you are reading data from here. So what you put last, it will come first. So this is called last in, first out. So note down this abbreviation. So last in, first out. So the first letter is D. Okay. If you're reading further, okay, it will go down. Your top will go down. Okay. So D is get eliminated. Now top become 2. Now you are getting D, A. Then you are deleting this. Okay. The top will go down. Again, you'll get that. So if you're getting this same input, it will go for accepted state. So this is one example. Now what I'm doing, okay, instead of dad, if I'm giving cat, so this is the given input. So C will go first, okay, A will come next, then T will come next. If you're reading this, okay, again T will come first, then A will come here, then C will come here. So it will go for rejection. So this is for simple understanding I am explaining. Definitely I'll share, don't worry about this. So if you want to define pushdown automata, it will work with finite automata with stack. Okay. And add a stack provides memory. So your stack will act like a memory. It will store your data. It will increase the capacity of your machine. It will help to do operation. Okay. So only the context-free grammar is recognized by PDA, not a regular language. Okay. Regular grammar. So this is the definition of language. So A to the power n, B to the power n. So you can add n number of symbols. So this is the generalistic form. Okay, where n is always greater than or equal to 0. So according to that, you can write a different kind of combination, different kind of operations. So again, we're going to see in different way. So we are reading input symbol from the tape. So this is the input symbol reading operation. Then we need to perform stack operation. Okay. So this is the stack operation. So always you need to follow or you need to monitor top of your stack. Okay. So whatever if you are inserting into a stack, that is called push operation. Okay. So whatever if you are taking from your stack, that is called pop operation. So this is like insert. I'll write over here. This is like insert. This is like reading, or you can say deleting. Okay. So this is the operation. You can empty your stack, like emptying your entire boxes of books. Okay, then you can know where is the location of your top pointer. Okay, so before doing any operation, you need to know where your top pointer is located. So this is top pointer. So you can say like top pointer. Okay, if I am writing, you don't know where I am locating, but if I am taking this pointer, you know where I am locating. Okay, same way. If the pointer is over here, it is in level 2. If the pointer is over here, it is level 1. If the pointer is over here, it is level 0. So I can write few examples. Imagine if stack is empty. Okay, where your pointer will be? Pointer will be in 0 level. So this is top pointer. Okay, so from here, if you try to do read operation, it is not successful. If you try to do read operation, it is not successful because your stack is empty. Imagine if your stack level is 3, if the capacity is equal to 3, This is your stack. Your stack contains the word DAD. Okay, the capacity is T, and the pointer is top pointer is pointing to top level, top of your stack. Okay, if you try to push more item to over here, like an example of adding X over here. So this operation will get failed. Yes, piles of book you can consider like a stack. Okay, if you try to push a new word, new letter called X, then this operation will get failed because it will overflow. Okay, so before doing any operation, you need to know the position of your top. Otherwise, operation will get failed. Okay, so you have control unit. So control unit will read and write data from your stack. So each time if you are doing any operation, it will make changes in your machine. Okay, so each and every time we need to repeat this procedure until the entire string gets scanned. So there are 3 stack operation: pop operation, which will delete topmost element in the stack. So this is the example. So if you have pen and paper, you can work it out side by side instead of passive listening. So if you have pen and paper, please write this stack. This is the stack. So what happens if you do pop operation from the stack? Can anybody tell? Put in the chat box. It will remove A exactly because the top pointer is located in top of your stack. Okay. So what you will get alternatively? So A is removed. You will only left with B, A, Z0. Exactly. Now what happens? Your top pointer is realigned to B. So whenever you remove from stack, okay, your top pointer will get reduced by one level or one element. So this is before pop operation. This is after pop operation. So second operation is push. It is like inserting or writing in your stack. So where it will write, it will always write top of your stack. Okay, so this is top of your stack. This is before push operation from the previous operation. Okay, again if you are writing A over here, it will do over your B. So this is after your push operation. So all of you able to understand pop operation and push? I hope so. So this is sequential. This example is sequential. Okay. So next you will do NOP operation. It means no deletion, no insertion at the top. So it is like pass operation. So it will not do anything into your stack. It will retain as it is. So it is equal to pause button. So in tape recorder, we have pause button, right? It will not do. Okay. It will retain as it is. So sometimes you need to pause or hold your operation, right? During that time, you can choose NOP. Sometimes you need to wait for another input. So during that time, you can do like this. So next, we're going to see about transition function. So we'll have multiple states. So the first one is current state. Always you need to know what is the current state. So that is called QY. Okay. Next, you need to have current input A. Okay. So each and every time you need to have input symbol. Okay. So top of the stack will be represented by B. So this is the top of the symbol. Okay. So whenever you do, the transition will happen from I, it will change into J. Okay. So each and every time the stack content also changes. Okay. So what is the input? BA. What is the input? BA. So until are you able to understand what is the meaning of QA? QA is current state. Okay. What is the current input? Current input is A. If you are giving input A, then top of the stack will get changed. Top of the stack will get changed. It is moving to B. So what is your current state? It is B. Okay, B0. Okay. So if you are giving input A, current input A, okay. So you are doing push operation. You are doing push operation. So QY now going to change with input A. Okay. Now going to change with input A. So no A will get pushed and also top pointer also get changed. So this is after push of A. Okay. So the first one is your input. The second one is top of your stack. So also top of your stack also get changed. Now it become AB. So this is transition diagram for push A. So go through this diagram slowly, step by step. Then you're able to understand this example. Any doubts, any question over here? I hope all of you able to understand this. Yes, push grow from low to high. So I can imagine it is like a bucket. If you are pouring more and more water, the floating object always hang in the top level or layer of your water. So can imagine top is like a wooden bar. Always it will float according to your water level. Great example. So no doubts. Shall we move? Shall we move? Okay, great. Yes, thank you. Next we can discuss about non-deterministic PDA definition. Okay, so it is defined by 7 tuples. So if you have more complexity in your design, the more inputs will come. So we'll have more inputs, much more complex, where Q is the set of states, sigma is set of input, and this symbol contains finite set of stack symbols. Okay, stack symbols, we have n number of symbols. Okay, K0 is initial state, and Z0 belongs to that symbol. I don't know how to pronounce that symbol. Okay, start of stack symbol, and each and every F will belongs to final state. It is a set of final state to the given number of states. Gamma, yes ma'am, gamma. Okay, so this is the transition function. If you do any operation, this transition will happen from one state to another state. So if you are not able to understand, don't worry. So this is the given definition for non-deterministic PDA. So I try to give different color. So if you are using different color for the purpose, I will explain. I will explain. So red stands for state, blue stands for input symbol, and yellow stands for stack symbol, and green stands for new state. Okay, I try to give different color for different aspects and different operations. So it will help you to learn easily. It will help me to teach easily. So this delta is the function. When you do any operation in your stack, this delta function will happen. So this is the function. Okay. So according to the current state, according to the input, okay, each and every state will change. It will go for next state. Okay, with the stack symbol. So this is the example. So P, A, Z, which will go for Q, comma, AZ. So I will give some time. I will give some time. So note down this sigma function. Note down the sigma function. So state, input symbol, stack symbol. Next state, stack symbol. So if you have pen and paper, please note it down. So this is the given example. This is the given example. So in this PDA, the current state is P. So after reading the input A, okay, the Z is top of your stack. So Z will indicate top of your stack. Then it will change into new state, which is called Q, which is called Q. So if you are giving A, then what happens? Z always follow A. Z always follow A. Can you draw a diagram for this? Can you draw a diagram for this? So I try to draw. I try to draw. So this is your stack. This is your stack. This is your Z. Okay. This is the Z. And what is the P? P is the present state. So what is the P? So this is the present state. Okay. So what is the input? Your input is A. What is the input? Your input is A. Okay. If you are giving your input, it means you are pushing. You are pushing A to your stack. Okay. So after pushing, what happens? After pushing, what happens? So A is inserted. Your Z is moved to one level. Your Z is moved to one level. Instead of writing here, I will write over here. So Z is moved to one level. So after push of A, then how will you define this state? You can define with the help of Q. So this is state transition. This is state transition happened due to this delta. This delta. Is it clear? Is it clear? If you have any doubt within this, you can ask me. Okay, fine. So if you understand this, you can do for this. Yes, Z is like a pointer. It is top of your stack. That is what I mentioned. Z is top of your stack. So this is example for push operation. This is example for pop operation. So this E will delete your element. Will delete your element. It means it will remove A out of your stack. If you are giving input E, it means it will take A out of your stack. So A is removed. Then what happens? Your pointer will go downside. Your pointer will go downside. Are you able to understand the second example? The first one is for pushing. The second one is for popping. Or you can say it is a reading operation. So do this. Do this. Example 3. Again A is pushed. Again A is pushed. Now you are removing. Now you are removing. So these are the 4 examples you can work on. You can work on. So I'll give more practice example. I'll give more practice example. So this is another format. This is the another format. You can have different notation. Okay. So the present state going to change into state Q. So we have 2 inputs. The first input is your symbol A. The second input is called your stack pointer Z. So after giving this is the state transition. So this is your input. This is your stack pointer. Okay. So this is P state. So when you do transition, okay, you will get final result in such a way. So this is different form of notation. So try to do for the second diagram. Try to do for the second diagram. So this is for push. This is for push. This is for pop. So what happens when you try to delete A? When you try to delete A, the A will go. The A will go from your stack. Are you able to understand the graphical representation? Okay, great. So this is one more example. So the current state is A. Okay, the input is O or 0. Okay, the stack pointer is Z. So once you give, it will go for new state called 1. So it is repeating. It is repeating. Yes, same state, same state. So transition function is based upon current state, your input symbol including E, top of the stack. Okay. Reading input with NOP operation on stack. Okay. It will retain in the same state. Yes, retain in the same state. So let's see an example for this delta function. So Q1 followed by B followed by A. Okay, it's going to produce Q2. Yes, I will give break. Thanks for reminding. So I'll put in chat box. Sometimes the participants will get. For 20. What is the time? 4:12. 4:17. Hello all, we will start now. Let me share my screen. This is where we left. This is where we left. Okay. So we will visualize transition function in PDA. So it is based upon three factors. One is current state. The second one is input symbol. The third one is top of stack. Okay. So first we are reading input with NOP operation on stack. So reading means it will not disturb your data. So data will retain as it is. Okay. So this is the transition function. So Q1 followed by B followed by A. So Q1 is starting state and Q2 is ending state. Okay. Transition state. Where B is your input, A is your top pointer. Okay. So Q1 is current state, B is current input, and A is top of your stack. So if my screen is not visible, you try to rejoin. So is my screen visible for all or only for few? Yes, it is visible. So if it is not visible, please rejoin. Please rejoin. Quickly rejoin. I will wait for 1 minute. Yes. So I stop my screen, resharing. Sometimes it will happen. Okay, fine. So Q2 is next state. Q2 is next state. So this is the point, this is the status of your stack. So before NOP operation, imagine if you are doing NOP operation. So what is the meaning of NOP operation? Just your reading, just your reading. So if you are reading, nothing changes in your stack. Okay, it will retain in the same level. It will retain in the same level. So that is why pointer is pointing to A. So no changes. No changes. Okay. Okay, fine. So next, if you are deleting a element from your stack, okay, you are reading input, but you are doing with delete operation. So there is a minor difference. So the previous one is just reading, okay, without deleting. But the second one is reading but deleting. So what is the symbol you need to use for delete? Okay, so you need to give epsilon. You need to give epsilon. So Q1 is current state, B is current input, A is top of the stack. Okay, A is the top of the stack. Q2 is next state. So if you are doing delete operation, what happens? Your top stack will get changed. You are deleting A from your stack, you are reading, right? So that is why you need to give epsilon. Are you able to get the idea? So if you want to delete, you need to give this symbol for delete. So this translation function is converted from Q1 to Q2. Okay, fine. So next we're going to see about push operation. Next we're going to see about push operation. It means inserting an element to your stack. Okay. So this is the given function delta Q1 comma A comma B equal to Q2 AB. So Q1 is current state, A is current input, B is top of your stack, Q2 is next state. So this is the stack status before inserting your data. So it contains only B, A, Z0. If you push A one more time, if you push A one more time, okay, now it is pointed to top of the new stack. So any doubt within these three functions? So I'll recall one more time. So first one is NOP. First one is NOP. Are we discussed? Yes. The first one is NOP. Okay, no operation. The second one is POP. Okay, you're reading with delete operation. The third one is you're pushing, you're inserting your data. So only in NOP, the stack pointer retain as it is. Okay, if you do pop, it will go downside. If you do push, it will come one level up. So we'll have some examples. So to obtain a PDA to accept a language, L with the defined grammar. So if you are doing PDA, definitely your grammar should be context free. So note down. So if you want to PDA, so what is the condition you need to have? Okay, your language, your grammar should be context free. Context free. Otherwise, you cannot do PDA operation. Okay, so what is the grammar given? A to the power n, b to the power n, for condition n greater than or equal to 1. And what are the alphabets? Alphabets could be A, could be B, and it is a closure operation. So closure means you have all kind of possibilities. So this is the solution. So it will generate A to the power 0, B to the power 0. But what is the condition? It should be greater than 1. So this is not permitted. Okay. So what is the next possible combination? A to the power 1, B to the power 1. So which will yield this string. Okay. So next A to the power 2, B to the power 2, which will yield this string. So likewise, you can keep on increasing the value of n. So is it clear? Is this definition clear? Are you able to recognize? So here I will mention n equal to 0, a to the power 0, b to the power 0. Okay, this is impossible because of this condition. So n equal to 1, n equal to 2. Yes, thank you. So what are all the string combination which will get rejected? So look at the grammar. Look at the grammar. So consider if you are giving input, A, okay. So it will check according to your grammar rule. So your input is not matching with the grammar rule. So it should contain one A, one B at least. So this is first possible combination, right? So this is not accepted. This is not accepted. Suppose if your input is B, again A is getting missed over here. So this is also not accepted. So what it means, you need to have equal number of A, and equal number of B. So if you look at this pattern, you are able to recognize. So if you have uneven AB, it will reject. Okay, great. So check this with BA, whether this language will accept. Check with BA. Okay, check. Take it as example. Check. So we'll take example AABB. We'll take example AABB. Okay. So this is the initial stack 0. Okay. Stack is pointing to Z0. Right. So what is the input? Input is A. The first input is A. Okay. No, all these are rejected symbols. All these are rejecting symbols. Only these strings are accepted. Okay. Here you try to push the first element A into your stack. So you're pushing A. Your top pointer will go up. Your top pointer will go up. Okay. Now it will move to the next symbol, second A. Okay. If you are pushing one more A for your current stack, if you are pushing one more A for your current stack, okay, it will keep on increasing your pointer, top pointer. Okay. So what is the next input? Next input is your first B. If you keep on pushing B for your current stack, okay, then what you're supposed to do, you need to pop that A. You need to pop that A to write your B. So likewise, you are able to count equal number of A and equal number of B. Same way you need to do for B also. So how many times you are pushing A? 2 times. Okay. How many times B is existing over here? 2. That is why. That is why. If you have 2 A's, if you have 2 B, if you are checking how many push operations you are doing for A, 2 times push, 2 times pop, which means you have equal number of A and equal number of B. See, how many number of times you are doing push for A? 2 times. Okay. How many number of times pop you are doing for A? 2 times. The same go for B also, right? So I will explain one more time if you are not able to get in. So this is the given input string 2A and 2B, and you need to check whether equal number of A and equal number of B is there. Okay. So how will you check? You can check only with A or only with B. Okay. So there are four symbols. There are four symbols. Okay. So check with the A. Initially the stack is empty. So it is pointing to Z0. Okay. It is pointing to Z0. Right. So next what you are doing, you are pushing A. So what you are pushing A to your stack, your pointer will get increased. Okay. Next what you are doing, you are pushing A again. Now your stack pointer is increased. Okay. Next what you need to check, you need to delete the same A. So you are doing 2 times push. Now you are reversing that operation, 2 times pop. So it means it will contain equal number of A and equal number of B. So in this way, you're able to count. In this way, you're able to count. Because you have only two symbols, right? You have only two symbols. A is permitted and B is permitted. You can do for B also. You can do for B also. That is what I told. BA is not possible. So look at the grammar. Grammar only hold for A followed by B. A followed by B. You look at this pattern. Only A starting over here, not B. Are you able to get the idea? Great, great observation. So sometimes you'll get confused, don't worry. Sometimes you'll get confused. The same diagram, the same example, you can do with the this function. So we have lack of time. So what I do, I'll just share this material with you. Suppose if you are giving AB, your machine will reject. Your machine will reject. Okay, because your stack is not get emptied. Your stack is not get emptied. I think I can explain this also. Okay, so let us discuss this example AABB. Okay, so what is the input symbol? AABB. What is the starting state? Q0. What is the pointer of your top? Z0. Okay, suppose if you are pushing A, what it means, you are taking A out of your input. Okay, you will reach ABB. You will reach ABB. So I'm just drawing over here. So first operation, push A. So A will be here. Okay, now your pointer will have AZ0. Are you able to understand this one? Okay, great. So second, what you are doing, you are doing one more push. So this is the first operation. Second, you are doing one more push. If you are doing one more push, A is top over, okay. Your pointer is now moved to second D. Your pointer is now moved to second D. Okay. So what is your pointer? AAZ0. So next what you are doing pop operation. Okay. So what is the idea? Equal number of A, equal number of B. You're reading the first B, right? You're reading the first B. First B means you're popping A because A should be equal to B, right? So by reading the first B, you try to cancel the first A. So for this and this. So A, B means you are reading this B means you need to cancel the similar A. Now you are able to understand this, I think so. A, now our pointer is AAZ0. Okay. Now you are reading the first B. So first B means you need to do pop operation of A. Pop operation of A. Exactly, sir. Exactly. So in this scenario, so for this example, I am talking. Okay. Equal number of A, equal number of B. So if B comes, you need to delete one more A. So you are popping out A from this. You are popping out A from this. Now it will move to here. So now your pointer become A Z0 because you are popping out one more A. Now what you are doing? You are reading one more B. You are reading one more B. Okay, reading one more B means you need to do one more pop of A. Okay, now you are reading one more B. So A is taken out. Now pointer will go here. Z0, Z0. Now your stack become empty. Now your stack become empty. Okay. So finally, you reached empty stack. Empty stack means everything is compromised. So 2A means 2B is there. So string is accepted. So finally your stack should be empty. So you can think like borrowing book. So whenever you borrow book from your friend, you will keep a box in your home. Okay. When you are giving return back to your friend, you are taking from that box. If there is no books in your box, it means you gave all books to your friend. So there is no more books in your home. QF means final state. So Q0 means starting state. QF means final state. So try to do with AB, AB. So try to do in the same way, AB, AB. So first time you are pushing A, okay. Yes, second time you are popping A. So it is not completed, right? You are able to read only two strings. You are able to read only two strings. This tab become empty. This tag become empty. Within two operations, you ended up with empty stack. Are you able to understand? So any doubts within these two strings, acceptance and rejection? Okay, thank you. Yes, function is not completed. So look at the third example. Third example. So look at the grammar, what grammar will do. So WW, two characters, and you can raise to the power R, so it will do reverse order. Okay, so what are the two symbols? You have AB and you have multiple possibilities, all kind of possibilities. So in previous example, they mentioned AB. Okay, so in this example, they mentioned W. They are not putting any sequence. So that is why here you will have AA, okay, or BB, or AB or BA. But it should be in reverse. So that is what they are telling. It should be in reverse. So if you do AB, okay, if you do BA, will they are equal? No. So these sequence are not accepted. Are you able to get the point? So in previous example, we have a to the power n, b to the power n. So in this example, they gave w to the power r. R means you need to do reverse. You need to do reverse. So if you are giving a, okay. So one more symbol you might have, you might have a. So if you are doing reverse, what you will get for a, again you will get a. So that is why this string is accepted. So if you are choosing B, if you are choosing B, BB, if you are doing reverse, again you will get BB. Okay, so this is accepted. If you are choosing AB, if you do reverse, what happens? You will get BA. So this is not accepted. So it should be equal to the reverse order also. If you take A, B, B, A, okay, if you are doing reverse, what happens? You'll get the same sequence, right? A over here, B over here, B over here, and A over here. So which is equal to this one also, equal to this one also. So this is accepted. So this is belongs to, sir. So this word need to belongs to AB. So these two are alphabets. These two are alphabets. You can have only two symbols, A, comma B, in this language. So if you generate any word, that word should belongs to this alphabet. You cannot have ABC. So C is not in this language. It is not belongs to this language. Okay. So all these strings will get rejected. Yes, yes. It need to maintain the symmetry. Exactly. You got that point. So whatever the word you're going to produce with this grammar, it need to preserve that symmetry if you do in reverse. So do with the example of BAAB. Do with the example of BAAB. So try and tell me. So initially the stack is empty. The pointer is over here, top, Z0. So first you are reading B. You are pushing B. Okay. Now what you are doing? You are pushing A. So A will come over here. So top pointer will point to A. Yes, R means not power, it is reverse. So that is the difference. R is reverse operation, not power. So if you push, if you are encountering one more A, then you need to do reverse operation. So this is the logic. Okay. Then only you need to identify whether it is symmetry or not. Okay. Now we are encountering one more B. Now what are you supposed to do? What is supposed to do? You need to pop. So if you do, stack will become empty. So it means this string is accepted. It is in reverse order. So in simple terms, B, A, B. You are writing B to your stack, it will go down. Okay. Again, if you are pushing A to your stack, it will go down. Again, if you are pushing A to your stack, it will go down. Okay, top. Again, if you are writing B over here, it will go top. So these all about push operation. Okay. When you read this, the last item will come first out. So B will come first. Okay. A will come next. Okay. Again, A will come next. Again, B will come first. So these two are equal. So what we did, we reverse this word. Okay. That is why it is accepted. While taking from your stack, you are reading from the last position, right? It means the reverse. So according to your logic, you need to push and pop according to your logic. So in previous example, equal number of A and B. Here, it is not about equal number of A and B. It is not about equal number of A and B. The same string need to be in reverse order. You can take an example of AA. So first A will go for push. The second A will go for pop. So stack will become empty. So if you have doubt, don't worry. You need to work few more problems. So I will stop at here. I try to give one beautiful material. Sometimes we'll get confusion while studying TOC. It's normal. I'll share one material called Dory Mick and Universal Machine. So it is a comic book created by one professor. So you can Google. You are able to get this PDF. I'll share this link in chat box. You can download book from this link. So this is the beautiful book. So in the meantime, you can read this book tomorrow. So Monday we can discuss about this content. So look at the review given by the topmost persons, including Bill Gates. Okay, Scott Harrison, one of the important key person in quantum computing. Okay, he's the professor who maintaining complexity zoo. I already shared in this link chat box. So this book created by David Evans. So he wrote a book for theory of computation also. Okay, he dedicated this book for his daughter. If it is not visible, plus wait for a minute and try to rejoin or refresh. Are you able to see the content? So go through this. We will discuss on Monday. Yes, very nice material. So if you understand this, you can understand the essence of a theory of computation. Yeah, thank you all. Thank you. I will share slides, don't worry. I will share very important things. I will delete remaining unnecessary contents. Creating PPT for POC is especially challenging. We need to use more and more graphical or we need to write. So I prefer both. Yeah, thank you all. If you go through 3-day content, you will get a lot of idea. If you have so much of doubts, please revise the content as much as possible. Take pen and paper and work it out. Then you will get clarity. Always use Canvas. So Canvas is very good platform. You can have video, you can have this material also. So WhatsApp, most of your content will go up. So you don't have continuity. Accidentally, the content will get deleted. So always use Canvas. More than 10 people, 20 people, WhatsApp become inefficient. I'll share the whole content. Sir, push and pop, we need to decide based upon that language structure, grammar. So compare these two examples in this video, rewatch this video, definitely you'll get clarity. It is listed in that slide, sir. The grammar is defined in that slide itself. L of G, okay, L of G, it is discussed over there. Link already shared in chat box. Please refer this. I hope other participants are able to get that link. I shared in chat box, sir. Yeah, thank you. For others, they are saying yes. The coordinators will answer this question, sir. Thank you also. Shall we wind up? So if you have any doubt, you can contact me. You can message me. I will share my social media ID.
Thank you, sir. We
Thank
will
you, sir.
meet tomorrow, 3 p.m.
Tomorrow
Monday.
means Monday.
Monday. Okay.
Okay, sir. Thank you.
Thank you, sir.